Welcome to all of you. What we're going to do today is I'm going to kind of recap cellular respiration. So I've actually gone through content basically from 1 to 5. I've already given you kind of a summary lecture on the introduction, which was content 1. Today is kind of summarizing what I'd like you to go over from 2 to 5, which is really aerobic cellular respiration. So cellular respiration, which we use oxygen to break down glucose basically into ATP. So I'm just going to shrink this down here. And we're going to go through just kind of the presentation that I gave in class, and it kind of gives a good summary of what I'd like you to know for cellular respiration. Okay? So here's the big idea with cellular respiration. You're going to bring in glucose or food. It can be protein. It can be a number of things. We're going to really kind of just focus on glucose. Then you bring in oxygen by breathing. And when we bring these two things in, we're going to convert them into CO2, water vapor, which we breathe out. And then this is the big thing that we want, which we want energy, okay? And we want usable energy, and the usable energy that we have is ATP. Okay, so this is kind of just a figure. I like this figure because it basically shows that, you eat the food, the glucose goes inside your bloodstream. So here's our bloodstream right here, okay? But we can't do cellular respiration in our bloodstream. We have to bring the molecules, the macromolecules, in this case glucose, out of our bloodstream and into a cell. Okay, and then this is where cellular respiration is going to happen inside the cell. And it's really going to happen in two areas. Okay, our first phase, which we call glycolysis, is going to happen in the cytoplasm. Okay, so here's in the cytoplasm. It's just inside the cell, floating around. The first process is going to be converted from glucose to pyruvate. Okay. All the rest of the steps are going to happen inside the mitochondria, our power plant of the cell. But the very first step, okay, the first step of breaking down glucose happens outside the mitochondria, and then we move into the mitochondria. And I'll clarify that as we go through here. Okay? So we've already kind of alluded to talking about photosynthesis and cellular respiration. Again, these are the two big processes that we're going to go through in Unit 2, and really the only processes that we're going to go in Unit 2, and they relate really well together. They're complete opposites of each other. So photosynthesis is an unbelievable reaction, which plants can take CO2 and water, and then they take energy, and they use this energy to combine these two molecules together to create glucose and then oxygen. Okay? Now, plants are the only things that are able to do this, also cyanobacteria and some types of protists, but we as animals are not able to do this. But what we do, as well as plants do it, and every living thing does it. So some people forget that plants do cellular respiration, but every living thing has to do cellular respiration. It's the only way to create energy. So what we do is we take glucose, we take oxygen, we use the oxygen to burn the glucose in a very controlled combustion reaction, in which we produce CO2, water, and energy. And if you look, these are the exact opposite. The products of cellular respiration are the reactants of photosynthesis, and then vice versa. Okay, so cellular respiration is a process of turning chemical energy, glucose, okay, but we can also turn proteins and fats, but we like to talk about glucose originally, into free energy. And the free energy that we like to use in our body is ATP. Now, this is a catabolic reaction, just looking at some terminology from our very first lecture. Catabolic meaning that you're taking a large molecule like glucose and breaking it down into smaller ones. Now, we can do this two ways. Okay, we can perform cellular respiration in two ways. Aerobic cellular respiration. Aerobic means that we're going to have oxygen when we do it. So this is the best way of performing cellular respiration. If you've got oxygen, you're going to be able to create a ton of ATP when you burn glucose. Now, another way that we can do it, although it's kind of our backup plan, it's not really the best way of doing it because we don't produce hardly any ATP doing it, is anaerobic respiration. And that's when we try and burn glucose without oxygen. Now, that happens to us sometimes when we are working out and our muscles basically run out of oxygen, but we still burn glucose even though we don't have oxygen. And then we produce a nasty byproduct called lactic acid. Okay? Other organisms, instead of producing lactic acid, produce ethanol, but we're going to talk about that when we get into anaerobic respiration. Okay, so we got two ways. We've got aerobic with oxygen and anaerobic without oxygen. Okay, so aerobic respiration, it's a cellular respiration we humans do. Aerobic respiration has more been extensively studied because it's a more important process than anaerobic. Anaerobic is more of our backup. Okay, now because we use oxygen during anaerobic respiration, we can measure oxygen levels, and that really measures kind of our metabolic rates. If you wanted to go in and get your metabolic rate tested, what they're going to hook you up to is an oxygen sensor, and they're going to measure basically how fast you're processing oxygen. The faster you process oxygen, the faster your metabolic rate. The slower you process oxygen, the slower your metabolic rate. Right? Now I have a couple of links in here. There's some really, really good videos. I don't want to waste some time just watching them, but definitely when you download my presentation, I would take a look at these links. They're excellent. Okay, so let's go through aerobic cellular respiration. So cellular respiration with oxygen. And the big thing is there's going to be 4 pathways. Sometimes they leave out the pyruvate oxidation. They'll tie it into glycolysis. But in this course, we're going to have 4 distinct pathways in order to turn glucose into ATP. The first pathway is glycolysis, then pyruvate oxidation, then the Krebs cycle or the citric acid cycle, and then finally the oxidative phosphorylation. This is commonly called the electron transport chain and chemiosmosis. Okay, it's just the same name. They just call it different things. Okay, so let's go through just our general overall process here. So here's our 4 processes. We got glycolysis. This is pyruvate oxidation. Then we got our citric acid cycle or the Krebs cycle, and then the electron transport chain. And it's going to go in this order. Okay, anytime that we stop this cycle, it prevents the process from continuing. Okay, so a couple things that I want you to keep in mind when we're going through this. So the ultimate goal of respiration is to create ATP from ADP, adenosine triphosphate with the 3 phosphates, from ADP, adenosine diphosphate with the 2. Okay, ATP is not created in all pathways. Most is created in our last pathway right here, oxidative phosphorylation. That's where we're going to make almost all of our ATP. We do make it a little bit earlier, but this is where primarily most of it's going to happen. The other pathways primarily are used to create loaded energy carriers. And if you remember from our first lecture, I talked about NADH and FADH. Okay? And these are literally carriers of energy. Now, they're not carriers of usable energy. We want to carry this energy that's not usable using NADH as an enzyme that kind of carries it around, because it's going to be eventually converted into a usable form ATP. But the energy NADH and FADH2 is carrying, it's not usable. Okay, it's capable of turning into ATP, but that's what we're going to do is we're going to take the NADH from that was built up in these processes, and then in our last phase is when we're going to convert the NADH energy and the FADH energy into ATP. Okay. All right. And the last one, carriers eventually transport the energy to the last stage where most of it is converted to ATP from ADP. All right, so we're going to start with glycolysis. Okay, now this is a really good link. I have this on my link from yesterday's news feed. I highly suggest you look at it. It is an unbelievable link. It's the best link that I think I've found. Okay, so technically take a look at that. So here's glycolysis. Here's our first stage. Okay, so here's the key things we need to know for glycolysis. And I'm just going to move my thing maybe over here. So key thing is it happens in the cytosol. It's going to happen outside the mitochondria. Okay, so this just happens regularly in the cell, the first phase. Okay. The other really key thing is no oxygen is required at this point. So it can proceed with oxygen or without it. So when we're going through glycolysis, you're going to go through glycolysis whether you have oxygen and you're going to do aerobic, or you don't have oxygen and you do anaerobic. Okay. Glycolysis is always completed regardless of whether you have oxygen or not. Okay. The main thing it's going to do is it's going to convert one glucose molecule, which is 6 carbons, into 2 pyruvate molecules, which are each 3 carbons. So we're not losing any carbons here. Okay, we're not going to lose any carbons to CO2. No CO2 is coming off during this phase, because all you're doing is taking a 6-carbon sugar and then breaking it into 2 3-carbon molecules. Okay. Now, if you remember, our second law of thermodynamics states that when you go from something complicated, like a glucose, into something simpler, like 2 pyruvate molecules, because you've gone from a 6-carbon molecule to 2 3-carbon molecules, then energy's got to be released, right? There was energy used to create order, having those 6 carbons together, and now when you create a little bit of disorder, you're going to release a little bit of energy. So in this case, we are going to release 4 ATPs when we go from glucose to pyruvate. Okay, so we're going to release 4 ATPs. However, okay, this is important to keep in mind, to get this reaction initially started, to get this glucose initially broken up, we need to put in 2 ATPs. So before even respiration started, we need to take 2 ATP molecules and just get the glucose moving so that it breaks apart. Once it broke apart, it released 4 ATPs. So net, at the very end, we have a net result of 2 ATP molecules. Okay, because we put 2 ATPs in, it released 4. So overall, at the end of glycolysis, we've released 2 ATP molecules. And that makes sense because we went from a complicated molecule like glucose into simpler molecules. And when that happens, it's a catabolic reaction, releases energies. Okay? Now, it released more than just the 2 ATP energies. It also released unusable energy, okay, and energy that we want to eventually use. So we stored that energy on these carriers. And what had happened during glycolysis is we had empty carriers that weren't carrying energy at all. And we know they're not carrying energy at all because they're NAD+. Okay, so they've been oxidized at this point. They've lost their electron. They've lost their energy, so they've been oxidized. Okay? And we took some of the energy that when glucose broke down into pyruvate, it released some ATP, but it also released other energy that we trapped on these NADHs. So NADHs means that it's loaded full of energy. NAD plus means it's empty, doesn't have energy. NADH, that H is kind of, you can look at it as the energy. So now it's loaded. So we have two loaded carriers now. Okay? So we created 2 usable forms of energy and 2 unusable forms that will eventually be converted into ATPs. Okay? So at the very end, and this is what I need you to know, at the very end, you have 2 NADHs, 2 ATPs, and 2 pyruvate molecules. So you went into glycolysis with glucose, and this is what you left glycolysis with. Okay? And this is now going to enter into our second phase, which is going to be pyruvate oxidation. Okay? And this is kind of just an overview of what we're ending glycolysis with. Okay, so we got glycolysis down. The big thing was we went from glucose to pyruvate. Now we're going to go into pyruvate oxidation. Okay, and the big thing here is we're going to convert pyruvate, which is a 3, we've got 2 of them, so we're going to convert 2 pyruvate molecules into 2 acetyl-CoAs. Now acetyl-CoAs, each of them is only 2 carbons, okay, where pyruvate, each of them was 3 carbons. So we've lost a carbon on each pyruvate, and that carbon is going to go off as CO2. So let's go through pyruvate oxidation. Okay, big thing. We're now in the mitochondria, and we're specifically in the mitochondria matrix. Okay? Oxygen is required to perform this process. So once we have made our pyruvate, we've got to make a choice. If we have oxygen, we're going to go through pyruvate oxidation. Key thing is that we're oxidizing pyruvate because we have oxygen. If we don't have oxygen, we're not going to go through pyruvate oxidation. We're going to go through anaerobic respiration, which we're going to talk about after this. But right now, we're assuming that we do have oxygen, and now we're going through pyruvate oxidation. So this is going to happen in the mitochondria. Oxygen is required to perform pyruvate oxidation. The big thing is we're going to convert 2 pyruvate molecules, each of them that is 3 carbons, into 2 acetyl-CoA molecules by oxidizing them. Okay? And when we do this, the acetyl-CoA molecules are only 2 carbons each, where each pyruvates are 3 carbons. So 2 CO2s are going to come off, okay? Because we've lost 2 of the carbons from the original glucose molecule, which had 6. So now we only have 4 carbons left, 2 each in the acetyl-CoAs. Okay? That's what I have here. We're not going to produce any ATP during this process, but since we went from a pyruvate molecule, which was 3 carbons, so a little bit more ordered, into a 2-carbon acetyl-CoA, that must mean that energy was released. And it was released, but it wasn't released as ATP. It's released as that unusable form that we trapped using NAD pluses, okay? And they trapped the energy becoming NADHs. Okay? So we've got some more NADHs from this result. So some key things, that 1 pyruvate molecule creates 1 CO2 and 1 NADH, but since we have 2 pyruvate molecules, the end result of pyruvate oxidation is 2 NADHs. These are the carriers going to carry the unusable energy into the end result, which we're going to convert it to normal energy. I didn't create any ATP during this process. Okay, I did during glycolysis, but not during this process. And I created 2 waste CO2s and 2 acetyl-CoAs. And these are the molecules that we're going to be kind of sending into the next pathway. So we've done pyruvate oxidation. Okay, now we're going to go into the citric acid cycle, or the Krebs cycle. And this is kind of just loading more electron carriers with energy. We're just going to load up a bunch of more carriers. Okay. So this is still happening in the matrix. Okay. The big thing here is we're going to have acetyl-CoA that converts into citrate, and then it gets converted basically back into acetyl-CoA and then into citrate, and it's just a cycle. Okay. I'm not going to ask you all about the steps and the cycles. That's going to be something you have to memorize in university. Okay. Key thing that I need you to know is that each citrate is going to go through the cycle creating 1 ATP, 3 NADHs and 2 ATP molecules. Okay? So since 2 acetyl-CoAs enter the cycle, you're going to have 2 ATPs because you're going to have, each acetyl-CoA is going to be converted to a citrate molecule, and each citrate creates these. Since you have 2 acetyl-CoAs, you're going to create 2 citrates, and they're going to create 2 ATPs, 6 NADHs, and 2 FADH2s. Okay? For every glucose molecule that goes. So the big thing in this cycle is we're creating a number of loaded carriers. Okay, we created a little bit more ATP during this process, but we created a lot more carriers. Okay, we created 6 NADHs and 2 FADHs. Now, at this point is when we get rid of all of the carbons. So we now have nothing left of the glucose molecule. Okay, the glucose molecule, which was 6 carbons long, lost 2 carbons during pyruvate oxidation to CO2, and now after the Krebs cycle, it lost all of its carbons. All of its carbons are now gone, and all we've done now is converted glucose into some ATP molecules and then a whole bunch of loaded carriers. And we're now going to go into our last phase. Okay, now our last phase is where everything happens. This is where we're going to create all the ATP. So before we go into that phase, let's take a look at what we're going into that phase with. Okay, so recall that we have discussed several of the pathways so far. Okay, the main purpose is to create free energy in the form of ATP. ATP is made by phosphorylating ADP. Okay, and phosphorylating means just adding a phosphate. Okay, now when we go into this last phase, which is going to be oxidative phosphorylation, it's also known as the electron transport chain in chemiosmosis. This is where most of the energy is made. All the loaded carriers that we created in the other processes are moving towards this pathway, and entering this pathway, they're going to convert from unusable energy, which the FADHs and the NADHs are carrying, into usable form, ATP. Okay. Now this is what we're going into this pathway with. So from glycolysis, we ended with this. Okay, now I didn't put all of the things in here. I didn't put my CO2s in here. I kind of just put it in the important things that we're going to be using. So at the end of glycolysis, I've got 2 NADHs, so I've got 2 loaded carriers here that's going to be brought to the final stage. I've got 2 ATPs, usable forms. Okay, at the end of pyruvate oxidation, I didn't make any ATP, I only created NADHs. At the end of the Krebs cycle, I've got 6 NADHs, 2 FADH2s, and 2 ATPs. So total entering this last little process here is I'm bringing 4 ATPs, 2 from glycolysis and 2 from the Krebs cycle. I'm bringing 10 ADHs, okay, made from all of the cycles, and then 2 FADHs, which I made in the Krebs cycle. And we're going to bring all of these into the last cycle, oxidative phosphorylation, also known as the electron transport chain, and chemiosmosis. So the location is we've moved out of the matrix. We're now into the inner mitochondrial membrane. Okay, and the main thing here is all the NADHs and FADH2s created by the other pathways move into the inner mitochondrial membrane and donate their electrons to a series of electron carriers embedded in the membrane. Okay, so this is our final thing. So hopefully you're sticking with me here because we're just kind of ending up here. Our last phase. So all of these NADHs and FADH2s, all of the energy that this thing is carrying, okay, and again, it's kind of unusable energy. We want to convert it into usable energy. What this energy does is it allows us to actively transport, so going back to Unit 1, we're going to actively transport hydrogen outside of the mitochondria. Okay? So now we're going to pump all of this hydrogen outside the inner mitochondrial membrane. So what we have here is a gradient, and we actually have a double gradient. Okay? And what I mean by a double gradient is one gradient is the fact that we have high concentrations of H pluses on the outside of the mitochondrial membrane, and then hardly any on the inside. So there's a concentration gradient driving these hydrogens back in. Okay? That's one of the concentration gradients. The other gradient is there's what we call electrical gradient. Because it's super positive on the outside, because all these H's contain a positive, it's going to be negative on the inside. So there's two things pulling these hydrogens back in. There's going to be the concentration gradient and then the electrical gradient. Both of these things are pulling them back in. Well, when they come back in, we send them through a very special kind of channel, which we call ATP synthase. Okay? So what the FADHs and the NADHs, the whole point of them is to pump out a whole bunch of H pluses. Okay? So we use the energy that they're carrying to punch out a whole bunch of H pluses. And then when the H pluses come back in, they come back in through ATP synthase. And as they come back through ATP synthase, this little carrier molecule is able to convert ADP to ATP. And this is where we're going to create all of our energies. Okay? So we have a whole bunch of H pluses outside here. We got a double gradient. We got high concentration of H pluses, and we got super positive on the outside. On the inside, very low concentration of H plus, and it's negative. So there's two things going to be driving these H's in. So as these H's get driven in, they go through ATP synthase, which converts ADP into ATP, and then this is our usable form. Okay? So as the hydrogens flow down their concentration electrical potential gradient, they release energy into ATP synthase, and this is ATP synthase, which is going to convert ADP to ATP. And we're done. And now we've created a whole bunch of ATP. Okay? Now the last thing that we want to talk about is why we breathe in oxygen. So we need oxygen, one, to get pyruvate going, but the main reason why we breathe in oxygen is basically oxygen is a final acceptor of these hydrogens. Okay, so as these hydrogens get pumped out, when they get pumped back in, okay, final acceptor of it is oxygen. It's going to combine with the hydrogens to produce water. Okay, so that's pretty much everything that I wanted you guys to know. The last thing that I'm going to mention is we normally, although the maximum number is about 36 to 38 ATPs, we don't always produce that much, okay? And here's the reason why we don't produce always the maximum amount of ATPs, okay? A couple of the reasons is that some of the H pluses leak through the mitochondrial membrane without ever passing ATP synthase. So if we go back, okay, the H's are supposed to go right through here, but some of the H pluses will actually just go right through the membrane, okay? It's a rare event, but it will happen sometimes, and if the H pluses don't go through the ATP synthase, it won't have the energy to convert ADP to ATP. So if not every single H plus goes through there, then we're not going to make maximum amounts of ATP, and that happens. Okay? The other thing is some of the energy from the electrical chemical gradient is used to transport pyruvate from the cytoplasm into the mitochondria, and if it has to go against this concentration gradient, it's going to use a little energy to do that. And then the last one, some of the energy is used to transport ATP, which is the energy, out of the mitochondria and into the cytoplasm, because if the cytoplasm already has a bunch of ATP and we want to send even more ATP into it, we're going to have to go through active transport, which requires ATP. Okay. The last thing that I'm going to mention, I know I keep saying the last thing, is, well, what if we're not going to burn a carbohydrate? What if we're going to burn a fat and a protein? Okay? So fats and proteins can be converted into energy as well, and they're going to go through cellular respiration, but they're going to jump in through here at different phases. Okay? So glucose basically goes through the entire, from beginning to end. It goes through glycolysis, pyruvate oxidation, the Krebs cycle, and oxidative phosphorylation. Where proteins will kind of jump in, halfway through the process, and same with fats. So I'm going to describe the difference. So where proteins will jump in. Okay? So proteins can jump into here, and they're either going to jump into glycolysis, so kind of not at the beginning of glycolysis, but kind of halfway through glycolysis. Okay? And then they can also jump into pyruvate oxidation. They can also jump into the Krebs cycle. So proteins can really enter the cellular respiration cycle anywhere, not at the beginning of glycolysis, but about halfway through glycolysis and then anywhere after that. Okay? They won't jump in at oxidative phosphorylation. They'll really only jump in at pyruvate oxidation or the Krebs cycle. That's the main part that they'll jump into. They can jump into the end parts of glycolysis. Okay? Fats are a little different. So fats are going to be broken into two pieces, into the glycerol part, and then the fatty acid. And this is a triglyceride, and it breaks into two pieces. So here's our glycerol part, and then our fatty acids. So the glycerol will jump into cellular respiration in glycolysis. Okay? And then the fatty acids are going to jump into the Krebs cycle. So when we burn fats, they break apart, and parts of them will go into glycolysis, and the other parts will go into the Krebs cycle. And then those keep going through, and then the same kind of process. We just don't produce as much energy going through that way as we do through starting in glycolysis and going all the way through. Okay? So here's a kind of nice little figure. So here we have carbohydrates go through glycolysis, pyruvate oxidation, the Krebs cycle, and then etc. Where fats, the glycerol is going to be jumping into glycolysis, and then the fatty acids are going to go into the Krebs cycle. Here it shows that proteins, okay, can go into, it shows into the pyruvate oxidation. It can kind of show the very end of glycolysis or pyruvate oxidation, and then the other parts proteins can go into is the Krebs cycle. All right, and there's a couple other links that I suggest that you take a look at. Okay, this is kind of just textbook stuff with my textbook, but you don't have to worry about that. But I definitely take a look at those links. And that's it. Okay, so that's kind of our summary of everything for cellular respiration. I know it was kind of long, but cellular respiration is a big process, and I highly suggest you go through those links that I have in there and look at some YouTube videos. Type in glycolysis, type in pyruvate oxidation. They're really, really excellent videos, and it helps with this kind of complicated process. So I hope this was a really good summary. Okay, take a look at your assignments, because I'm going to be giving you an assignment a little bit later today, which is our first assignment on a metabolic toxin. Okay, so take a look at the assignments page sometime today. It may not be right away this morning, but I'm going to put up your first assignment, and it will probably be due in a week. Okay, but I'll have all of that in the newsfeed. Okay, thanks, and I hope this helped you guys out.